Hi, my name is Christian Feherek and my project is the traditional cryptanalysis learning tool. This project focuses on the cryptanalysis of the Enigma M3 machine. This was a cipher machine that was used during the Second World War. The project aims to create a learning tool that the users would use in order to obtain information about the Enigma and understand its algorithm. To achieve this aim, the objectives were identified. First, the first step was to get familiar with the cipher device itself and how it works. This required researching the machine components and looking up the algorithm itself. Then the next step was to explore existing systems. These systems already exist and talk about the Enigma machine. Some of them provide a useful graphical user interface where the user can encrypt and decrypt using the machine. Some of these were plain text explanation accompanied by graphs. The next step was to understand algorithm visualization in computer science. This was needed because the system builds on top of good algorithm visualization. The system tries to combine both user interaction with the machine, that means that the user would be able to encrypt and decrypt, and it would also provide a good algorithm visualization of the encryption itself. The final outcome of the project can be seen on the screen. After launching the application, the user is presented with a welcome window. This window briefly describes what the Enigma machine is, what are the components, and how it operates. This window also serves as a user guide for the user. It contains screenshots of the system so the user can see how different functionalities are available. The Enigma cipher machine is a substitution cipher. That means that one letter is substituted by another one. It works on the basis of electric signal. The machine components are the rotors. These can be seen at the top of the window. Then below that is the lamp board, and below the lamp board is the keyboard. When a user presses a key on the keyboard, another letter lights up in the lamp board. This means that letter G is encrypted into letter Y. We can notice that a letter on the keyboard appears, the letter pressed on the keyboard appears under plain text on the left-hand side, whereas its code appears on the right-hand side under ciphertext. When the signal travels through the machine, it first enters the plugboard. Then it goes through the rotors from right to left. It travels through the set of rotors. Then it is reflected by the reflector. It travels back through the rotors, through the plugboard, and to light up a key in the lamp board. After every single key press, the rightmost rotor rotates. That means it changes its position, so that after every key press, the machine configuration is slightly changed. And this is why a letter G can be encrypted into different letters. After every single key press, the machine changes, so that means that the signal traveling inside of the rotor changes its path. The user can configure the rotors by clicking on the Configure button. The user can select the different types of rotor and then click OK to apply the changes. The user can also make pairs in the plugboard. This can be achieved by selecting any two letters, then clicking Add Pair. The system handles invalid input in the following way. For example, a pairing up letter L with itself is not allowed, and the system responds to that. The user can also delete pairs by selecting them and then clicking the Delete button. Pressing OK applies the changes. The user can switch the view from the machine to the animation. This view represents the same machine components, but in a slightly different way. The rotors are represented by rectangles. A rotor has an inner part and an outer part. The inner part of the rotor can be shifted with respect to the outer part. This shift is called the offset. Going back to the machine and rotating the rotors manually will be reflected in the animation view. This offset can be seen at the top of the rotor. The user can select a letter for the animation. Pressing play and the animation begins. This animation shows the way of the electric signal traveling through the machine. We can see that the signal enters the rightmost rotor first, and it enters at the position of F. The inside of the rotors is in such a position that the character J on the inside is aligned with character F on the outside. This is because the rotors offset, and this means that the signal traveling through the rotor will travel through the wiring between J and Z. Once the signal is reflected, the color of the arrows and the inside wiring is changed. This is to indicate the change in direction. The user can pause the animation and go backwards or go forwards. The user can also continue the animation at any stage. By clicking on the same button, the animation is deleted and another letter can be selected for a different animation. Plain text explanation is also displayed at each stage of the algorithm. This can be viewed at the bottom of the page. If the user decides to go back to the machine during the animation and change its configuration, either rotating the rotors or changing the rotors, this would mean that the animation we just played is no longer consistent with the machine. The user is notified about the potential inconsistency. The color of the arrows and the lines is changed to blue, and there is a warning message at the bottom of the screen. The system also handles invalid input data. For example, in a plugboard, a letter that is already paired up cannot be paired with another letter. So, for example, the pair RB would be rejected because B is already paired with A. The system handles this correctly. Another example of this would be selecting a letter. Say the user enters a number, the system rejects this input as well. The traditional cryptanalysis learning tool was developed for users who have little or no knowledge about the Enigma machine. During the user evaluation, the participants were recruited according to this need. In total, 25 people have participated in the study. These people were asked to perform different tasks using the system. These tasks were, for example, encrypting, decrypting, and configuring the machine. Then they were asked questions that could be answered with the help of the learning tool. Every participant said that at the beginning of the study they felt confused and found the topic very difficult, but the animation helped them understand the encryption, and without the visualization they wouldn't have learned about the algorithm. This is a positive feedback, and it demonstrates how algorithm visualization can be used effectively. The user evaluation has also contributed to forming suggestions for future work. For example, a useful addition to the system would be to include different machine variants. For instance, the Enigma M4 machine could be added. The system could also improve the graphical user interface to better resemble the real look of the Enigma machine. Additionally, sound effects could be added to enhance user experience and give additional feedback. In conclusion, the project was successful in achieving its aims. The system supports user interaction. That means that the user can encrypt, decrypt, and configure the machine. The system also makes use of algorithm visualization by allowing the user to watch an animation of the encryption. This is what distinguishes the traditional cryptanalysis learning tool from the other systems. Thank you for your attention.